Hello AP Physics 1 students. Let's go ahead and get started in our notes with what would be a do now question if we were in regular school. So here I'm asking you to sketch a graph of maximum kinetic energy versus frequency for a photoelectric effect experiment. And then once you do, I want you to determine the meaning of what the slope of the graph would represent, as well as the meaning of the y-intercept and x-intercept. So go ahead and pause the video, think it through, sketch it out, and then come back. Okay, so of course one of our overarching themes we've been talking about all year long is relating graphs to equations. Anytime you're ever thinking about a graph, you always think about what equation is linked to it, and of course there's a photoelectric effect experiment, and so the equation here relating kinetic energy to frequency is this one here, Ke max equals HF minus phi, where phi is that work function idea, that minimum energy to get the electron out of the atom. And so you see we're plotting kinetic energy on the y and frequency on the x, and what's the shape of this line, of this graph? Well, I mean, look, it's clearly straight line. This is obviously set up as y equals mx plus v, and so we're going to draw some sort of linear graph. Now, a lot of you probably do something like this. I hope that you did not, of course, start at 0, 0, because we're going to have some sort of y-intercept. That's what this equation shows you, but this is still wrong. If you drew this, you're actually wrong. So let's see if you didn't figure it out. Pause the video and see what's wrong about your graph before I show you. Okay, so you correctly identify this as a linear graph. So you do a straight line and the y-intercept is not 0. That's fantastic. But you have to remember, this is not just an actual graph. This is not just an equation. It represents something. This represents the electron that's stuck inside the atom and then comes out of the atom when a photon hits it, just like the dog that was stuck in the well. You throw a rock in and the dog comes out. If the rock was big enough, if the energy of the photon is large enough, it gets the electron out. But remember, it also is possible you send the photon in and it's just not enough energy, or you throw the rock in and it's not enough energy to get the dog out of the well, in which case mathematically we got negative kinetic energies. And that's what we're saying here, is that you've got some frequencies for which there are negative kinetic energies, but remember, there's no such thing as negative kinetic energy. That doesn't have any meaning in the real world, and so really this should be a dashed line. So just erase part of it. That's the idea. You certainly still want the straight line to extend backwards to see where it intersects here to tell the meaning of the y-intercept, but you should not have a solid line there because that does not represent reality. Those frequencies would just not get an electron out. So you wouldn't have negative kinetic energy. It just doesn't work. So this is the proper way to show this graph. Okay, let's talk about the different facets of the graph. And so first about the slope. I mean, here's the y, this is the x. What's the slope? Obviously the slope is h. It's Planck's constant. Simple, which makes perfect sense because we have a straight line. You should expect a constant slope, of course, right? What about the y-intercept? What's that? Well, hopefully you've identified it as negative phi. Not phi? No, it's not phi, right? There's a plus sign, there's a minus sign, that's not phi. B is negative phi, just like I've shown here, right? It's a negative number because phi itself is a positive number. It represents like the depth of the well, the amount of energy, the minimum amount of energy the photon has to have to get the electron just to the edge of the atom. For that, the minimum sized rock I threw in to just barely get the dog to the top of the well with nothing left over. So phi itself is a positive number. This is in the negative realm. This is negative phi. Okay. What about the x-intercept? Well, that's this part here where if a frequency of just this amount would give a kinetic energy of 0, right? That's like the minimum sized rock that just barely get the dog to the top of the well. It's the minimum sized photon. That is the what's called the cutoff or the threshold frequency. Maybe you didn't know that term, but that's the general idea, right? The minimum frequency that just barely has tells the photon that has enough energy to get the electron just to the edge of the atom without anything left over. Okay, before we leave this, I want you to add something to the graph. So imagine we do a different photoelectric effect experiment with a different metal that has a different value of phi. Phi, the work function, is a property of the metal itself. So let's say this particular value of phi is a smaller number than whatever phi is for this particular metal. So I want you to pause the video. I want you to sketch what the graph would look like if we have a different metal in the same experiment, but the value of phi is a smaller number. Okay, so if phi itself is a smaller number, that means that negative phi is going to be a number that's closer to 0. So negative phi prime, if you want to call it, is going to be up here, but still has to be a straight line because of course that's the equation shows you. And since the slope is h, does h change because we change the metal? No, it's Planck's constant. This is a universal constant, right? So it's going to be a line that's parallel, but shifted up or shifted to the left, however you want to think about it, right? Because the value of phi is a smaller number, so negative phi prime is then closer to 0. Or you can also say that the new cutoff or threshold frequency is a smaller number. It doesn't need as much energy to get this electron out of the atom. All right, let's shift over to try some practice problems in your notes packets. So let's take a look at numbers 3 and 4. Go ahead and pause the video, try everything on your own, then come back to see some answers. Okay, so for number 3, obviously we're talking about a photoelectric effect experiment here. It refers to photoelectrons, but there's nothing special about photoelectrons. They're just plain old electrons that just happen to be produced in a photoelectric effect experiment. So we know we're going to be dealing with this equation, Ke max equals HF minus phi. One of the big hurdles in this topic is recognizing when we're dealing with objects and when we're dealing with bundles of light energy, right? So the Ke here, this is the kinetic energy of the electrons themselves, bits of matter. HF, that's the energy of the photon, a bundle of light energy. We're pretending it's like a particle. That was Einstein's big achievement here at the time, right? And F, of course, the frequency of the light, which is kind of weird, right? In this part of HF, we have both the wave properties of light mixed with the particle properties of light. And then, of course, we have phi. That's what we're looking for, the work function. So we rearrange. Well, first of all, we realize that we're given the wavelength, right? So immediately we want to replace F with C over lambda. So it's HC over lambda minus phi. And then rearrange phi equals HC over lambda minus Ke max. And now it's a good time to start putting numbers in. Keeping in mind, of course, the other hurdle is that we want to make sure our units line up because, of course, this is in nanometers. Also, remember, you're going to pick your value of H that's going to make sense with whatever other units you're dealing with. Ke max, of course, is 1/2 mv squared. And here's where you really have to be careful with your units because if you just put in 1/2 mv squared, where we're dealing with electrons, so you know the mass of an electron, you're given the speed here, what units will 1/2 mv squared be in? That's going to be in joules, isn't it, right? Which means if you're going to do this, you have to make sure you're picking the value of H that's in joule seconds. So is that the 6.63 or the 4.14? That's the 6.63. But then you also have to worry about the fact that lambda is in nanometers, right? So you have to worry about all those things. You can get your answer of phi in joules. Alternatively, you could say, wait a second, like that HC here, and HC is that other constant, right? We already calculated what that's going to be. That's 1240, but then what are the units? Well, it's electron volt nanometers, which are great because this is in nanometers. You don't have to do any unit conversions at all, but it's in electron volts, which means then you have to take this value, 1/2 mv squared, that's in joules, and convert it into electron volts. So it's going to be a trade-off. You just have to choose your, pick your poison, whichever you want to do. At some point, you have to convert something from electron volts to joules or joules to electron volts. I'll give both answers here. Most times, you probably want to answer in electron volts. So we get 1.83. However, if you did in joules, you get this, 2.93 times 10 to the 19 joules. Really, neither one is preferable. Most times we answer in electron volts, so since the problem never said what units to put your answer in, it really doesn't matter. Choose whichever one you like better. All right, another photoelectric effect problem here. Letter A, just find the energy of the photons. We're just doing E photon equals HF. Nothing special here, but once again, we are given the wavelength, so immediately we're going to write this as HC over lambda. And lo and behold, here's HC again, so it probably is a good time to use the shortcut of 1240 electron volt nanometers. And then this is already in nanometers, no need to convert any units there. We're going to get 2.0 electron volts. However, you know what? If you want to be a little contrary and say, you know, I don't want to do that. I want to use H in joule seconds, the 6.63 value. And then, of course, you see 3 times 10 to the 8th meters per second. And then lambda, you do it to convert in nanometers, you're going to get this, 3.2 times 10 to the 19th joules. It is a 2 sig fig problem, right? 2 sig figs there, 2 sig figs there. If you give a third sig fig, okay, but why, right? You're obviously given 2 sig figs in the numbers in the problem. All right, letter B, you want to find the maximum kinetic energy of electrons in electron volts. Well, now it's the time to use the 0.4 volts, which is the potential difference needed to stop the emitted electrons. What's the name for that? Ah, yeah, that's stopping potential. That's V sub S. So now is the time to use this equation, Ke max equals EVS. And as we've done before, there's the easy way and the hard way. Which do we want? I think we want the easy way, right? The whole point of using electron volts is saying that these are electrons and it took 0.4 volts to stop them. Then, of course, how much energy do they have? They must have had 0.4 electron volts, right? You don't have to show work for that. That's why we use electron volts. It's so much easier. Now, if you wanted to put in the numbers here, we know the charge on an electron. You could do that, and you have the stopping potential. You could find it in joules. It's just that number's a lot more cumbersome, right? So I'm not sure there's a really good reason to do that, although actually there is. Right here, it did say to do an electron volt. So if you did find it first in joules, then convert it to electron volts, I'm sure we'll get something very similar. All right, for letter C, you want to find the work function. So here's our equation, Ke max equals HF minus phi. We're rearranging for phi. That's HF minus Ke max. And you could put all the numbers in, but why would you do that when we already have HF? We found it. And we got Ke max. We found that too, right? It's just 2 minus 0.4. That's going to be 1.6. However, if you really want to, you can certainly put it in joules as well. Here it doesn't say what units to put it in, so either one is absolutely fine. But I just think electron volts are easier because, they are.